Welcome back to your favorite review session. That's right. Okay, thanks for joining the online world. We do have a couple people there, so that's good. I'm also recording this, so I will post this on YouTube after it's rendered and uploaded. You'll see it there as well, so hopefully it can be of use to you going forward. You should see my screen, and yes, it does work well. So what I'm projecting here on the screen, everyone can see on the board behind me, and also the people in the online world can see the same thing, so there you go. Here we are at a review session for the exam tomorrow. Like I said, the exam tomorrow is 2 questions, and it's based on sort of the most recent stuff, but generally is cumulative, okay? And kind of the big topics are combined loading, stress transformations, and also stress concentrations and safety factors, okay? So that's also part of this. Wasn't really included in the practice problems, but is also kind of part of this class. So keep that in mind. Maybe we do just a kind of a quick review. 5-10 minutes here of general ideas, and we could start with just generally like stress concentrations. Okay, remember that if we have some discontinuity in a material, or fillet or something, rounded edge, stress can be amplified. Okay, so the El Clasico example is sort of a rectangular plate with a hole in it, and we provide some load here. Here's P. And we have some general dimensions for this that we provided. We typically label this with a capital D. And then this dimension here would be capital D minus R. And we generally label this as, 2R. Is my eraser not working? Minus 2R. And sometimes we call this dimension little d, all right? Where R is the radius of that hole. In the state of tension, we'd say that stress amplified near hole as sort of the max stress in this region is some concentration factor K times what you might consider sort of the nominal, or what we call the average stress. Where in this region, the average stress in the vicinity of the hole would be sort of in this portion of this particular member is just going to be P on little d times T, where T is the thickness of the plate into the page. Got that? And so generally, our stress gets amplified from the average value, which is kind of what you might consider your axial stress to sort of be in that region where that hole lives, you know, sort of this reduced area here of this particular piece, here and here. That gets amplified in the region of the hole to a value of K times that sigma average. And so the stress distribution generally is like quite amplified in that region relative to the other areas around it. So you might see a distribution that looks a bit like this for the stress around that particular hole. Okay, so this is for one specific case with increased stress from tension, but we could also have similar ideas from torsion, from bending, and we saw examples of all of those types of things in homeworks and practice problems and etc. And the actual stress concentration factor, this K value here, it comes from geometry only. So it's independent of material, and it just strictly comes from geometry. And so you see all these kind of funky charts. Let's see if I can pull some of them up here from the old notes. You get all these funky charts that show kind of what is this stress amplification around the vicinity of the hole or the fillet or whatever the case may be, given the geometry that you have. So I'll pull some of those up here and we can just take a look to remind you what those look like. Is that we have here's something that looks like this. Here's the drawing that I just made, basically, kind of showing that maximum stress amplified near the hole. And we got all these charts that look a bit like this. So this was the idea basically for tension. is what these stress concentration factors look like. And here they depend only on geometry, the radius of the hole, and the full width of the piece for this guy. And for this sort of like double filleted reduction in width, it depends on not only the width of the large portion, but the width of the small portion and also the radii of the fillets. So you can read charts like this to determine what the amplification factor will be. And remember, you're always amplifying the average stress in that region. All right, so the smaller reduced section, okay? So calculate what the stress would be sort of in this reduced section here, or for the case of the plate with a hole, this reduced section here, and then amplify that particular value. So we saw this for axial loading. In this case, we also have charts like this for torsion and for bending. Any questions about stress concentrations? Yeah, I think it's a relatively straightforward idea. Just got to be able to kind of like read the chart well. Okay. All right, that's that. Next, we talk about safety factor. I'm going to just try to do a quick review here. Okay. All right, a safety factor is just a number that's used in engineering to design to help you protect against failure. Okay. So the general equation is something like the allowable stress is either the yield stress, which we label as this like sigma capital Y, over SF, where SF is the safety factor. Or if you're protecting against ultimate stress, you might see the allowable stress that you're going to permit as the ultimate stress normalized by the safety factor. And that's really all there is to safety factor. Applicable both in normal stress and shear stress. So if you're protecting against some torsional something or other, you're probably going to use the safety factor for shear of some number, and so on and so on, okay? So if you happen to know the yield stress or happen to know the ultimate stress and you want to protect against that, normalize that yield stress or that ultimate stress by the safety factor, use that as your new allowable, and continue on your way. Got it? Not much more to safety factor than that. Any questions on safety factor? What industry might you think has a low safety factor? What's that? Space. Why space? Yeah, because weight really matters. So if you have a very high safety factor in general, that means that your piece is thicker than it needs to be, or somehow larger than it's protecting against more than what you need it to protect against. So it's going to be heavier. All right. Bad for aerospace because you want to have like really light mass and et cetera. What industry might you expect a very high safety factor?
Biomed.
Biomed? Yeah, I like that. That's good. Anything human life related that is not humans going to space. Or Formula One racing. So roller coasters at a theme park, probably pretty high safety factor, okay? They don't want any sort of liability on the roller coasters, right? Okay, so there you go. Those are some good examples. I would like to say like general commercial vehicles would have a higher safety factor just because I like to think that I'm safe, but they're also pushing for fuel efficiency these days, so that makes me nervous. So there you go. Okay. Any other questions on safety factor? Okay. The last kind of series of topics all kind of jive together. And that is like, we talked about bending separately from transverse loading, but these all kind of feed into this whole idea of combined loading, right? And so that's kind of the last general topic that we discussed. Combined loading. Our powers combined. Anybody? We are Captain Planet. Who said it? All right, Lars. Good job. I don't know if I was getting too old for Captain Planet references. Captain Planet was like this cartoon that I watched when I was a little kid. All right, so like early 90s. Was it still on when you guys were kids? Yeah, okay. Yeah, like barely. He's like, yeah, I don't really remember that. Okay, combined loading. The general idea here is that we're going to look at some portion of a piece that has multiple loads on it, and you could have stresses that develop in a piece from a variety of different loads that are formed. And so generally you might say that like some axial stress is a summation of, or some normal stress is some summation of some axial contributions plus some bending contributions, and that your shear loading generally is some shear loading that might come from torsion, plus some shear loading that might come from transverse shear. Okay? We've spent about a week on each one of these individual terms alone, okay? That's why I say I think this exam is like the culmination of this class, because combined loading basically uses everything that we spent so much time on in one problem. Okay? So, probably should know your combined loading. Just wink, wink, hint, hint, nudge, nudge, okay? Know your combined loading. And you're probably going to get all four of these pieces in there. So, know how to do them all, okay? Right? It won't be on there yet. It won't be on there. Yeah, okay. Sure, yeah, it won't be on there. No, okay. You don't need to study it. Yeah, go ahead. All right. So generally, we could have some axial loading, which we know is something like P on A, plus some bending, which I'm just generally going to label as MD over I, where D is some distance away from the center. This is, distance term could be Y, could be Z. We've seen a lot of like variables in this space for a position length. Typically, we use my over I, but D is denoting here a distance. It's a little bit better. For torsion, this is going to look something like TR on J, where T is the torque, R is the distance from the center of the circular cross-section, J is the polar moment of inertia, plus transverse shear, we saw something as like VQ on T, where remember that Q is this really weird kind of thing, which is A prime, Y bar prime. And so if we just take a second for that idea, it's that, all right, for transverse shear, we got some point of interest here. We've got some load coming across the surface. Well, we want to split that particular cross-section at the point of interest, define that width at that particular location, perpendicular to the load as the variable t, and then the area above or below, doesn't really matter, is A prime, and then the distance from that line t to the centroid, which is here this Y bar prime. How's that coming through? You read that okay? How's the board? Is the board all smeary? Do I need to erase it? Is it okay? Okay. All right. So that Q is that weird variable, but just remember A prime, Y bar prime. You'll have a list of centroids tomorrow, so, Y bar prime for a circle if you haven't kind of committed to memory of this half circle, 4R on 3 pi. Hopefully you commit that to memory. If not, it's going to be on the equation sheet, so you'll have that, okay? You may also just understand that we're doing almost entirely circular cross-sections in this class because this derivation for torsion, TR on J, is only for circular cross-sections, right? So when it comes to a circular cross-section, there's a really easy way to calculate Q. If you're sort of at one of these points that's right in the middle of the cross-section, then A prime, Y bar prime, which is Q, is pi on 2 R squared times 4R on 3 pi. And this actually simplifies quite easily to 2/3 R to the third. I wouldn't mind seeing that on some of the tests tomorrow. I know where you got that. All right. Makes life easier. So the general strategy when it comes to combined loading is typically you'll see loads, moments, torques, whatever, applied at various locations on the bar. And so the strategy for these relocate forces and moments. To cross-section centroid containing points of interest. And then use these guys. Got it? And when you're using those, make sure that you're monitoring and keeping track of the directionality closely. Okay, so just remember the subscripts on your stress. First subscript being the face on which you're acting, the second subscript is the direction. So be very mindful of that. Also, careful with directionality. And so the subscripts associated with the stress, you just have to be quite careful about. Yeah. Questions on the combined loading? We're going to do a couple of examples. Probably one good long example of combined loading here. Just a second. Jensen. Not quite sure what you mean. Yeah. Yeah. So the question here from the audience is, when you're relocating forces from one portion of a body to another, do you still need to include the original relocation of the force? Is that your question? And the answer is yes. That's kind of how the force couple works. Let's have a little aside here for just a second to clarify Mr. Jensen's question. World famous, say it with me, mechanics potato. That's right. And let's say we have 2 points on this body. Point number 1, point number 2. Okay, let's say A and B. All right, let's say that we have some force on A that is capital F. All right, and we want an equivalent force couple system at B that represents what's happening at that portion of the body if we needed to pick up that force at A and relocate it at B. With me? Okay. Well, we have a position vector that locates A from B. Here, this is position vector locating A from B. And I'm not violating any rules of law if I also write at B 2 forces that are equal and opposite to each other, which are F and F. You guys familiar with that letter, right? Right. Okay, so these forces are equal and opposite to each other at B, right? And the general idea here is that this force now here and this force might be considered a couple. Did you guys learn about couples in your statics class? Forces with equal and opposite magnitudes that are parallel to each other form a couple. And the magnitude of the moment created by that couple is whatever the magnitude of that force is multiplied by the magnitude of the distance between them, right? Got that? So I can eliminate these guys from the current situation by drawing a moment, which is the position vector arriving at A from B crossed with that force at A, right? That is this couple that you've created, okay? So redrawing my figure, I get rid of this guy and this guy, and what's left over at B? The same original force that was at A. Got it? But now I also have to include the couple that's generated from picking that guy up and moving it over to B. So I've eliminated whatever was going on at A. This F still remains because it wasn't part of the couple that I'm going to represent with a moment here in just a second. And then I also have sort of the resulting moment here that gets generated from this equation. So this is exactly what we're doing every time that we pick up a force and put it at a different location in the structure. We do this, but cut out the silly drawing of all the extra forces and stuff like that. Got it? But this is, a concept that goes back to statics about like an equivalent force couple system at another portion of a body is represented by placing that force there and also accommodating the R cross F required to do that. Got it? Okay. Other questions? Go. Yes. Okay, so we have a question here about the directionality associated with a torque term. Okay, so let's consider a cross-section of a circular member that might have a torque on it. It's been a while since I've like used this writing pad regularly, so my handwriting's a little suspicious on this, but apologies for that. Okay, hopefully you can at least still sort of read it. But let's say that we have like some circular cross-section, and I'm kind of looking at it from the side here. Let's say we have a couple of points. Let's say A, let's say B, and let's say C. We'll leave D out of this for now. And let's say we have a coordinate system that's kind of our typical coordinate system for these guys. X down the center of the shaft, Y up, and Z kind of off to the left here. Right-handed coordinate system. Don't you forget it. Okay. Now let's say that we have a torque on this guy. It could either be plus or minus X. Let's just generally take a positive torque. So here's some torque in the X direction. All right. So the double arrow, remember, indicates that this is a moment or torque that's being applied. And if I want to understand how this torque is being applied to this cross section, I'm going to use the right-hand rule by sort of putting my thumb in the direction of the double arrow. So in this case, I'm kind of putting my thumb in the direction of TX and sort of rotating my right hand. And in that particular case, I'm going to see what generally wants to be like a rotation of this cross section in this general direction from that torque. Okay, it's trying to like turn it this way. We all kind of like see that general idea? All right. So if I'm interested in the directionality of the shear at any particular point on the outside of this cross section, I want to know what directionality that torque imparts load at that particular location. Okay? And the way that I do that is I'm thinking about like the tangent to the circle at the point of interest. Okay? So I'm generally like rotating or moving around this guy in this general fashion. And so anywhere where I come off of the oval or I come off the circle, I'm going to have direction in that particular tangent. So I will have some direction of shear at point C in that orientation, some here at B in that orientation, some here at A in that orientation. So let's talk about what each of these shear components actually is. Now, we know that generally our subscripts on shear, IJ, would be the I face, J direction, right? So what about point A? Well, all these are on the X face, okay? X is the outward normal here, so it's on the X face. And generally this arrow here is pointing which direction? Someone give it to me. Negative Y. So this is a tau XY at A and generally is negative, okay? It's because it's on the plus X face minus Y direction. Got that? We can continue this idea for the other points. Here, tau X at B. I know I'm on the X face. What direction are things happening in B? Z direction, okay? And positive or negative? Yeah, this is generally going to be a positive. Hey, yeah, like a lag here. This is the plus X face and the plus Z direction. Lastly, point C, tau X, Y, generally positive because we have positive X face and we have positive Y direction. Got that? You're kind of coming off the tangent of the circle with these torques, okay? Doesn't necessarily really have to do with the positive or negative value of the torque itself, because this is generally a positive torque, but is producing a negative shear at A. So you want to get away from the idea of a positive or a negative torque being associated with a positive or a negative shear. Because on opposite sides of the bar, for instance, at point C, you have a positive tau xy, and at point A, you have a negative tau xy. So you get a positive or negative shear from a positive or a negative torque. You know, you got to get away from using the positive or negative value of the torque for understanding the positive negative. There's more to it than that. Got it? Okay. Other questions? Okay. Last thing I want to talk about quickly is some of the stress transformation stuff. and principal stresses is that if we have a state of stress at a particular point, we could represent that state of stress with our stress cube, right? So remember what this looks like. Looks a bit like this, and you could have all of your sort of components of this guy, right? You could have some normal stress in Z, normal stress in X, normal stress in Y, and you could have all your associated shear stresses. I'm not going to draw them all in here. I think we kind of know all of them, right? But this is the general idea of your stress cube. Could have shear on the X face in the Y or Z direction, the Y face on the X or Z direction, and the Z face in the X and Y direction, okay? So we have these 6 shears, and we also have 3 normal stresses, 1 in X, 1 in Y, 1 in Z. When it comes to our stress transformation equations, in this class, we're only doing 2D transformations. So in this class, when it comes to stress transformation and principal stresses, we're assuming that our stress cube has one face with no stress, okay? It's de-stressed, right? So in this class, 2D states of stress. That means that one face has no stress. Normally, and by convention, we're assigning the Z direction as the face with no stress. It's just kind of naturally how you would do it because you typically want to work in the XY plane, right? So usually Z face. Okay, so that means that like anything associated with the Z direction and these guys, you know, equivalents tau xz and tau yz, all 0. Okay. So what that leaves us with is one face of this cube that has no stress. And so if we actually think about what that means for this stress cube here, well, that means that, well, all the stresses that were on the Z face, goodbye. Okay, they gone. All right. And their associated counterparts, oh boy, it's gonna be hard to do. Oh, got it. Ooh, got it. Nice. Okay. Their associated counterparts are also gone, right? So tau yz and tau xz also gone. And this leads us with some view of this cube down the z-axis where you would only see, if you're looking at this from the side, a sigma x, a sigma y, and a tau xy. So looking down z, I'm just trying to do this kind of fast. You just have this general state where you can only see the normal stresses on the x face, kind of looking at it from the side, normal stress on the y face, looking from the side, and the shear stress on this like xy face or yx face, however you want to think about it, that you can see. And this here is the 2D stress element, or the 2D element of plane stress, and tends to happen on the surface of materials, the surface of bars. That might be, you know, something that you see for combined loading, maybe. Okay? So this is our general 2D stress element. And remember that this is a representation of orthogonal cuts that we make in our structure to expose these particular surfaces so that we may calculate the stresses. Got that? So anytime we look at like the cross section of a bar, we're like making an imaginary cut through like a plane and exposing a face. That would be like one face of the cube. Got it? We could also cut this way, expose a different face, and cut this way and expose a different face. Those orthogonal cuts make up the stress cube. And those cuts that we made were sort of arbitrary, and we could also make different cuts in different directions. And those alternate cuts might lead to an alternate coordinate system that would be like an x prime, y prime coordinate system. But I thought I plugged this in. Oh no, I just plugged in mine. Can you hook a brother up? Okay. And if we know that there's a rotation angle between a coordinate system that we originally used, x, y, and a coordinate system that we're moving to, x prime, y prime, well, we can utilize information that we may already have about this 2D stress state to calculate a new stress state in a different coordinate system. And that would look something like sigma x cosine squared theta plus sigma y sine squared theta plus 2 tau x y cosine theta sine theta. We have alternate equations too for sigma y prime, slightly different, and also tau x prime y prime. You got some equations there in your equation sheet, but we derived them all using that 2D stress element and slicing through it and doing an equilibrium balance. Okay, so we have all these transformations that get us from some slices that we made to other slices that we might make. Just like that, right? Okay. And they look like this. They're functions of theta that utilize constants that we've already determined in the xy coordinate system. So sigma x, sigma y, tau xy, these are constants now. And our new sigma x prime, sigma y prime, tau x prime, y prime, these now are alternate stresses and alternate coordinate systems, which are a function of theta, which is just a variable that tells us what our rotation angle is between the coordinate systems. So these guys here are functions of theta. Okay. And we know that using calculus, we could determine the maximum and the minimum of these particular functions if we take derivatives, set it equal to 0, and solve for the value of theta, which kind of solves these guys. Okay, so find min max by d theta equal 0 for any one of those particular functions, right? Out pops the values of theta, which maximize or minimize your function, and then plug those back into the original equations for either principal stress or max shear stress, depending on which function you started with. Got it? Okay. Results in, I will draw it this way, principal stresses. Which might look like something like sigma P1 and P2. You might also just see it as sigma 1, 2. This is also another way that it's represented. Is going to be the mean stress plus or minus the maximum shear stress, where the mean stress is sigma x plus sigma y on 2. And the maximum shear stress is the square root of sigma x minus sigma y on 2 squared plus tau xy squared. Capiche? Okay. Rotation angles that you need to get to principal stresses and maximum shear stress, they're also gotten from this derivation. Looks like 1/2 tangent inverse 2 tau xy over sigma x minus sigma y if you're doing principal stress. And the shear would be similar to that, 1/2 tangent inverse of sigma y minus sigma x over 2 tau xy, I think is what it is. Yeah, okay. Those ones are hard to kind of keep straight in your head, but somehow I stare at them long enough. Okay, so that's that. And that's pretty much all we learned. So we could have just had one lecture for 40 minutes and just, been on our way. Okay, questions about principal stress and stress transformations. Jensen. The sign convention, like the subscripts? Yeah. So question about the directionality of the shear. Okay, let's look at this arrow. This very finely drawn arrow. Okay? This is on the positive x face in the positive y direction. You got that? So positive, positive, positive. Cool. Let's look at this arrow. He's on the negative y face in the negative x direction. Negative, negative, positive. This guy, negative x face, negative y direction, positive. Positive y face, positive x direction, positive. So all these arrows indicate a positive shear stress. And it's giving this pinchy, boop, boop, to this particular element. Got it? It's giving this shear, this pinch that we're so familiar with, that would deform it by our strain information into, you know, this rhombus shape that maybe you remember from like week 5, right? Okay. Good. Other questions? Okay. That was a mini lesson that was not supposed to go that long, but went that long. Should we do example problems? Okay. Let's pull up the review sheet. So if I haven't, oh, by the way, Morse circle, nothing. Don't expect anything on Morse circle. Less is more, you know what I mean? Yeah. Okay. So here are your practice problems. If you can't tell, combined loading is the thing for this class. Okay? If you can walk away and do combined loading in this class, you can basically do everything. I mean, it's everything. So your 3005 professor will be very happy with you if you know how to do combined loading. I guarantee it. Just like who's the guy that does the Men's Warehouse commercials? You'll like the way you look. I guarantee it. That guy had like a falling out with the company, actually. He founded it and they like kicked him out of the company. It's a really interesting story, actually. Okay, read about it on your own time. Anyone have a question they want to look at? Do you want to look at number 2 because it's complicated? Yeah. Seems like lots of people want to. Did you want a different one? Dawson wants a different one. Are you gonna? Okay. All right. So what about number 2? Like, was most annoying? Okay. Solving for the shear at which point? B or A? I guess this kind of doesn't really matter all that much, but okay. This one is particularly tricky because it's kind of an open cross section. We hadn't really talked all that much about calculating the Q value for an open cross section. But I put a challenge problem on there, so let's tackle the challenge. Okay, so I'll pull this picture in here, and then we'll copy it down, and we'll do it. And let's look maybe just at like point B. Is that okay? Because that's where, I mean, you're going to get transverse shear in both A and B. Okay, so here's number 2. We've got this guy here, and let's just try to find stress state at B. Okay. So we got a little bit of a wonky coordinate system on this problem, but it really shouldn't throw you off that bad because it's still a right-handed coordinate system, and you just got to know that you're looking at the negative x face instead of the positive x face when we do this cross section. Okay, that's really probably the best strategy to go about this. So just like every other combined loading problem, the first thing you want to do is pick up the forces and relocate them to the cross section of interest. Okay, so what we want to do is relocate F and M to AA, this cross-section that we have there. Okay, so if we sort of do that, we'll pick up our force and just place it directly. We're going to have to do a little bit of trig to get there. This is going to be, here this 50 pounds has some components in both the y and the z direction. So here this looks like 50 times, what would this be? Cosine 60 in negative j plus 50 times sine 60 in k hat. Y'all cool with that? So let me get up my numbers here. Okay, so this will be something like negative 43.3 j hat plus 25. Sorry, minus. The z direction is to the right. I'm sorry. So this is minus 25 k hat pounds. Okay, so this force here sort of being down at the left would indicate a negative z and a negative y component. Yes? Okay. All right, so that's that. And now, when we pick that force up and we relocate it to the cross-section AA, we're going to get some moment that develops. And that moment is something like the position vector, which locates that force from that cross-section, crossed with the force that exists there. And be mindful now that we're always pointing to the force from the cross-section of interest. And so this position vector here is our position vector R of interest. In this case, it's going to look like negative 10 in the I hat direction and positive 12 in K hat. So here, this position vector, negative 10 I hat plus 12 K hat inches crossed with this force, which is just right here. Got that? Okay, so do your cross products, execute them well, draw yourself the determinant form if you need to, whatever you got to do, and you'll have 520 I hat minus 250 J hat plus 433 K hat. Okay, and this is going to be inch pounds. How are we doing on all that? Gavin. Oh, yeah, I'm sorry. Yep, that's correct. It's going too fast for my own good. All right, apologies for that. Yeah, the 60 resolves to the z. Been a long day. Apologies. Thank you for the correction. Yeah, but this is all, the rest of this is correct. Okay. So here we are with our forces and our moments. So these are the guys that we want to draw in this particular cross section, this force, this moment. Now we take those forces and good to make a sketch of the cross section. So sketch. Of AA. And we're specifically interested in this point over here, which is point B. And let's make sure that we put our coordinate system in here and we draw it accurately. Okay, so back up to the figure. We have the X going sort of in the backwards direction, Y up and Z back. So here we have something that looks like X, Y up, and the Z backwards. Okay. It's not my aim to sort of trick you with some weird coordinate system tomorrow. Just giving you that, but it's good to go through this problem anyway to have the discussion. Okay. So in general, this face that we're looking at here, what face is this? This is the negative X face. And that's because like the normal that comes off of this face is the negative X direction. Everyone understand why this is the negative X face? Yes, this is an important concept because it really drives all the subscripts for all the stresses. Okay. Was that a no for Mr. Lamb? Okay. Was that a no? No. Yes. Okay. So this is the negative x face. So let's put all of our loads in our moments that are sort of acting on this particular guy, and let's talk about what effects they're going to have at point B. So our forces first, we've got negative 43.3 j hat and minus 25 k hat. So this negative 43.3 j hat, this is kind of coming all across the face. I'm going to draw this nice and big. Big force across this face, 43.3 pounds. Okay. Big force. Rawr. Okay. All right. We also have this negative 25 k hat, so that's going to come streaking right across this face like this. Rawr. I'm back. Guess who's back? Back again. All right, we're still recording. We okay? I just lost internet for a second there, but we're back. Okay. So let's think about the contributions that each one of these guys is going to particularly have. And what I really want to think about is like this transverse load and this transverse load. Very frozen. Back from the shadow realm. Yes, I have returned. I had weird internet there for a second. And so when I think about each of these transverse loads, Hi.
Welcome.
Guess who's back?
Made her back.
All right, there we go. We're back. Again. So we're continuing on with our shear term. We're looking at the torsion now. 520 inch-pounds. This is generally acting to provide a rotation of this cross-section that looks a bit like this. It's trying to rotate generally like this. Fancy. Mike Sevier approved. Definitely not. Okay. But generally, it's going to rotate the cross-section in a direction that looks like that. Yes? So what does that mean about point B? Well, it means we're going to get off the highway at point B and generally going to be pointing in that direction. Yes? Okay. So what face are we looking at? Negative x. And what direction is this moving? Positive y. So we should have like a negative sign here. 250. Oh, sorry, 520. Inch-pounds multiplied by a radius. 1 inch. This is the location of our point of interest. So again, we need to have a clarification here. This variable r is the location from the center of the cross-section. Okay, the center of the cross-section generally is here, right in the middle. Okay, my point B is the radius away from there. Okay, so I don't need any like 1 minus 0.75 in this case. It is 1 inch away from the middle. And then this all by pi on 2 times 1 inch to the fourth minus 0.75 inch to the fourth. In the case of the polar moment of inertia, it is a geometric property of the cross-section as a whole, so I would have to include its contributions. So calculating the shear stress tau xy, we get negative 484 inch-pounds from the torque and 62.2 from the transverse shear. Inch-pounds, no, just pound. PSI, geez. 62.2 PSI. All right, so all together, everybody in together now, keeping with the Wu-Tang theme. That's just negative 422 PSI. That's it. Oh, my handwritten solution says negative. No. Sorry about that. The handwritten solutions are correct with the negative sign. Apologies for the handout. Okay, questions for the shear stress? Feeling okay? All right. Let's do the normal stress. We sort of skipped over it, but I think it's the easier of the two. This could be something like P on A plus M, let's call it D, over I. This is generally what we're going to look at. I guess before we go there, let's actually look at tau xz. It's probably important to discuss this. What about tau xz? Here's a hint. If your outward direction is the free surface of the material, no shear stress. That's your hint. So in this case, tau xz is also tau zx. So the shear stress on the z face in the x direction. If the outward normal is the surface of the material, no stress. Okay? Not that important to like know that right now. You can go through and justify yourself with the normal routes that we've been going through. But here the outward normal at point B of the surface would be generally the z direction or negative z direction. That outward normal is a free face, no stress. But you can go through the same methodology that we've been going through before, and that you could have some contribution from transverse shear, and you could have some contribution from torsion. Okay? We already talked about torsion. We're getting off the highway in the y direction at B. So tau xz, nothing from the torsion. Got it? My transverse shear. Here's where we got to talk about what it means to define this variable t. Because when we looked at the transverse shear for this 43.3 pounds here, this is a force that's coming across the y face. And we define the variable t as the thickness at the point of interest perpendicular to that transverse load. Got it? So when it comes to the force that's coming across the face in z, this 25 pounds here, I would want to try to define the thickness variable t perpendicular to that load at the point of interest. So perpendicular to that load at the point of interest is basically a line here with no thickness at B. It's a point, okay? I can't really draw a thickness variable there, a T. It would be a point, okay? What's the area above that point? 0. So this term goes to 0 because Q goes to 0, because A prime is 0, okay? Is that clear? All right, we've seen that example a number of times now, so hopefully that's okay. But in this case, tau x z is 0. Cool with that? Lastly, my normal stress. All right, do I have any axial loading on this particular face? What do you think, Mr. Freyer? No. My loads are only in y and z, which are acting across the face, so I don't have any x directional force. Got it? Now what about moments? Do have a couple of moments here. I got this 433, and I got this 250, right? One of these contributes normal stress at B and one does not. Which one will contribute normal stress at B? The 250. What kind of stress is it going to contribute at B? Compression or tension? Compression. All right, the way you want to think about this is take that cross section, pull it out of the paper, and then bend around the double arrow. Okay? That's how I think about this. Pull that cross section out of the paper, try to bend around that double arrow. You're going to get this tension on this side that contains point B, right? If I thought about doing that same thing for the 433, okay? Pull this out of the paper, try to bend around that 433. Yeah, okay, I'm going to get compression on the bottom, tension on the top, nothing at B from that. Got it? All right, pull it out of the page, try to bend it around 250, bend it this way. I'm going to get tension all along this back fiber of that bar. Got it? So, should get a general positive value from that 250 and nothing from the 433. So here, 250 inch-pounds. The distance, again, is this the radius, outer radius. And the area moment inertia, pi on 4, 1 inch to the fourth minus 0.75 inches to the fourth. Okay. Yeah. Work this all out. What are my numbers here? Got to find them. Is that right? Yeah, top in tension, bottom in compression. What's that? Yeah, tension on the negative x face. So it's a little misleading here. So how do we justify this mathematically? Man, we have an anomaly here. I don't know if I've ever had this before. Ah, that's because we're in the negative z direction. So the distance that we take is a negative z value. Okay. Yeah. So yes, this value should be a negative, and this actually makes this a positive. Yeah, because we're on the negative x face, negative z direction. Yeah. So it should be a tension. It should be a tension. So the value actually listed in the solution is wrong. We're having a tough day today. This should be a tension. Yes, we're on the negative x face. Yeah. So we'll have a negative, but we're on the negative x face. Yes. Correct. Because we're looking at the negative x face and we get a negative stress value here, that would indicate a tension. Yeah. Don't worry. No crazy cross sections. No crazy coordinate systems tomorrow. It's all very straightforward coordinate systems. Yeah. Tough. All right. How are we doing in internet land? We still alive?
Good.
All right, good. All right, let's move along. All right. That gives you a I mean, those are hard. I'm not gonna lie. I picked some hard ones. Like this one is much more reasonable. Like, come on. If you can do this one, your life should be good. Good? Okay. Well, everyone's like, all right, I felt good about that one. Okay, that's good. Maybe I was like, yeah, I felt good about that too. Yeah. It's like, yeah, sure did. How are you feeling about stress transformations? To me, these are really kind of just plug and chug. You just got to make sure you get the angle right. Right?
Yeah, can you go over the angle and figuring out
Yeah.
what the angle is? Because I know in the homework, at least the ones that I was doing, I just kept messing it up because I got the wrong angle.
Yeah, no problem. Okay, so we have a question from the online audience to go over one of the stress transformation ones, make sure we got the angle right. So let's just take this first one because this is sort of like this inclined plane problem. Make sure that we get the angle right for our transformations. All right, so this is number 4. Appropriate for today that we're doing number 4. May the 4th be with you. That's right. Okay, so no coordinate system given for this one straight away, but we're going to just maybe assume that we're going to work with that. Reasonable. Okay. So we're asked for the normal stress and the shear stress on this inclined plane AB. So I want normal stress and the shear stress on the inclined plane. We would typically label that as the NT shear stress, normal transverse shear stress on this inclined plane. And to get there, we're just going to use stress transformation equations from our coordinate system that we see here, this XY that we've defined, to some coordinate system related to this sort of ramped surface. All right. So on this particular surface, I'm going to label this as my normal direction and label this as my tangential direction. Not clear? And then we're going to solve for sigma n and tau nt. Right? So the way that you want to do this is you want to isolate either the top component or the bottom component. I think easier to look at the bottom component because the angle's already there for you.
I have a quick
And
question.
question from the audience. Go ahead.
How did you decide whether the normal goes up or like upwards or downwards? How'd you decide which way your normal vector is going to go?
So the question is, how did I decide the normal vector was up or down? Well, it actually depends on how you slice the piece. So if I slice my ramp like this, my normal to that ramp is here.
Okay.
If I slice my ramp the other way, looking like home plate here or something, then my normal is here.
Okay, I see. Just goes away
Okay.
from the face.
Right.
All right, thank you.
So we're going to take a look at this since we kind of have the angles associated. So this is the normal tangential. We're given this angle here of 30 degrees. And on this like normal tangential general coordinate system, I want to put my original coordinate system that I sort of had defined, my x and my y. that I normally defined looking something like that. So just put these coordinate systems right on top of each other. It's going to help you sort of, with your stress transformations, to just lay them over the top of each other and just look at the angle that was required to get there. Good. All right. So then the question is, well, what's the angle required to go from XY to NT? Is it 30 or is it 60? Who says 30? Raise your hand. Who says 60? Raise your hand. Okay, 60s have it. Okay, if I convince you that this 30 degrees is the same as this angle, yeah? And that this must be 90 degrees, then this has to be 60. Okay with that? All right, it's probably the easiest way to see it. Okay, so once you've kind of gotten to that, we know we're going to use stress transformation equations. And typically those stress transformation equations would look something like sigma x prime equals stuff. But in this case, we're not rotating from xy to x prime y prime. We're rotating from xy to nt. So instead of labeling the new stress as sigma x prime, I'm just going to label it as sigma n. Got that? But we're generally going to use the same transformation equation. It's just slapping a different label on it, okay? It's like calling a busted car a brand new, used, slightly, whatever. Call it whatever you want, CarMax. It's a piece of crap. Call it whatever you want, all right? You're not fooling me. Here, this is going to look something like sigma x cosine squared theta plus sigma y sine squared theta plus 2 tau xy cosine theta sine theta. Got it? This is our general stress transformation equation, and so then we just have to define the angles appropriately. This is the single angle formulation. You could also use the double angle formulation, which is on the equation sheet. Are they both on there or just the one? Just the double angle? I should put that one on here? Is that what I use in the solution? No, you want this one on the equation sheet, or you want me to use the double angle and the formulation? Okay, this one's easier to memorize. Just memorize this one. Come on. Just memorize it, Nick. God. So the last things that we have to take care of here are making sure that we get these guys right. Once you get those guys, do the equation. Sigma x, what do we got in this case? -3. Got to make sure you get it right here. Why is it -3? Well, here we have, again, thinking about the face and the direction. This is the positive x face generally, okay? The outward normal to that face is in the positive x direction. And this stress is generally acting in the negative x direction. So the negative and positive together give me a negative. On the other side, we could view it the other way. This is generally the negative x face. The outward normal to that face is negative x. And this stress is generally pointed in the positive direction. Negative x face, positive x direction, negative sigma x. So however you slice it, always comes back correctly. All right, sigma y, 2, generally positive. And now the shear stress at 4 KSI, positive or negative? Negative. My angle rotating from x to nt, 60 degrees. Be on with your business. -2.7 KSI. How are we doing with that? Feeling okay?
How'd you determine that tau was negative?
How do we determine tau was negative? All right, let's go take a look. So again, here, this face is the outward facing positive x direction. Okay.
Mhm.
Generally, this shear coming across that face is in the negative y direction. This arrow is generally pointing in negative y. So negative y direction. So together, the negative y and the positive x gives me a negative tau xy.
What about its counterpart on the other side, though, that points in the opposite direction?
What about its counterpart on the other side that points in the other direction? All right, let's look at this guy. He points in the positive y direction, yes? But this is on the negative x face.
Oh, I see.
Negative x face, positive y also gives me a negative tau xy. Got it?
Yes.
Okay. No matter how you slice it. Again, go back to the car dealership. Put some fancy sticker on there. I don't give a. It's a terrible piece of crap. I know what a geometro is. I ain't buying it. All right. We can also figure out tau and t from same transformation equation. These guys feed in. Calculate away. Got it? All right. How about the rest of these guys? Rest of these stress transformation guys. So a lot of these guys, again, are just plugging and chugging. Even the principal stress one, it's make sure you get your stresses correct. This is a positive shear stress. This is a positive sigma x. This is a negative sigma y. Just make sure that that is accurately labeled and accurately portrayed, right? And remember what we're looking at when we're looking at this two-dimensional element. It was once a 3D element that we have looked at now from the side, saying that the surface we're looking at has no stress upon it. Is a 2D element with no z direction stress, right? Just got to remember that that's how it was made. And when you're making these transformations, it's basically like cutting in a different way. Okay. How are we on number 6? Anyone try number 6? I mean, it really is just plug and chug when you get all the numbers right. Yeah. Cool.
I have
All right,
one
more question from the
about
audience.
Stress transformations. What's the difference between, so you said these are the double angle ones in the equation sheet, and
Yeah.
what's the difference between the two of them? Can you use them interchangeably?
The question is, what's the difference between the double angle formulation and the single angle formulation that we've been using? They are the same. They're related through trig identities, so they'll get the exact same answer.
Okay. Thank you.
You're welcome. Other questions? I don't remember the exact identity. It's like cosine squared theta equals 1 minus cosine 2 theta, something like that. I can't remember. All right, so number 7 is the big boy. It's the big dog. Anyone try to tackle this guy? Tried? What's that? It started? Yeah. Anyone else? All right, this is just the culmination of kind of everything that we've done. If you see a non-circular cross-section on the test, this is a non-circular cross-section. What would you assume will not act on this cross-section? Torsion. You could still have shear with some transverse loading. I'm not going to ask you anything about torsion of a non-circular cross-section. I'm not going to ask you to derive Prandtl stress functions from the test. Yeah. No. So in this particular instance, you see that these loads act right in the middle. You're not going to have any torque in this case. You're going to have maybe some bending moments, some transverse loads. That's all you got to deal with. Okay. So here we've got this general loading situation, and you're asked about information at this little point D here, which is an element on the surface on the top side, which is actually at a location of x equals 15 millimeters from sort of the center location. Got it? And so you tackle this problem the exact same way. We have general dimensions of this cross-section, and we're told that we have equal thickness throughout. All of these dimensions here are 13 millimeters for the web and the flange. Right. So let's take a look at the problem statements, and I'm just going to pull in my solutions, and we'll just talk about it as we go, okay? We don't have to do the whole solution written out as we go, but I think just talking about it is probably the best way to get through this. Okay. So determine the normal stress and shear stress at point D on the member. Okay, this is a combined loading problem, just like we've been doing all along. Pick up these forces, relocate them to the cross-section of interest. Okay, we'll do that according to this. we have some force on the end. It retains 9I negative 13J. We see that directly. And we calculate the moment that results from the position vector that locates that force crossed with that force. So here we have 4 meters in Z. This is 400 millimeter dimension. So that's our R bar. We're going to cross that with the force that exists at C, which looks something like 9I hat minus 13J hat. Got it? So when we execute, you get a bending moment at that location, which looks something like 5.2 I hat plus 3.6 J hat kilonewton meters after doing your cross product. Fine. So we make our cross section, we look at it, we have a couple of things going on. We have the bending moment 3.6 kilonewton meters, bending Newton 5.2 kilonewton meters. We have the 2 transverse shear loads, the 9 kilonewtons and the 13 kilonewtons. Okay. So we could have contributions from everything except torsion. Let's first look at the normal stress. The normal stress is kind of a combination here between the 2 different bending moments that could contribute stress at this point D. Now, we remember generally that normal stress can come from bending or from axial loading. And in this case, we don't have any axial loading. The Z direction is the long axis of the bar. So here we're looking at the XY plane, which is the cross section. So Z is coming out of the board at us. We don't have any forces in the Z direction, so we don't have any axial loading in Z. The only possible normal stress that we could develop is normal stress from bending. Got it? Strangely, in this problem, we do have a situation of bending about both the X and the Y axis, which will contribute normal stress at D. This goes back to a little bit of the eccentric loading that we sort of talked about at the end of the bending lecture, where if you have some point that is both off the Y axis and off the X axis, then you could have contributions from both MX and MY that provide normal stress. Got it? This is what we see here, is that this 3.6 kilonewton meters, this generally, if I thought about extending this guy sort of out of the page and bending around, is going to give us compression at D. Right? Now, when I think about this 5.2 kilonewton meters, if I pull this out of the plane and I think about tilting that upwards, that is also going to provide compression at D. So when it comes down to calculating the stresses from each one of these guys, we should see negative signs in both cases, which I've sort of messed up here. Man, not a good day for me. Yeah, so these should both be in compression. Man. Actually, no, the 5.2 tension. That was right. Man. Okay. 3.6 will give compression. Bend it around that 3.6. Yes, definitely compression. 5.2, bend it down because we're trying to bend around it downward. Yeah. Okay. Yes, that will give tension. Okay. So correct. Should be a plus sign here. This is correct as written. So here we have some positive contribution of normal stress from this 5.2 kilonewton meters, some negative contribution from the 3.6 because this is in compression. Do your math here, making sure that you're accounting for the distances appropriately. So here, this 5.2 kilonewton meters is going to provide bending around the axis that generally passes through the Y or the X dimension. And so point D is located at 0.0375 meters above this particular axis of bending. Okay, so this general dimension here is the 0.0375 meters, 37.5 millimeters. Now, D also resides a distance away from this bending moment, which is 15 millimeters, or 0.015 meters. Got it? All right. We have area moments of inertia. When we bend around the x-axis, we use IX. When we bend around the y-axis, we use IY. Those are given in the problem. Here, IX 5.1 times 10 to the 6 millimeters to the fourth, 14 times 10 to the 6 millimeters to the fourth. These have been converted into meters to the fourth through a conversion of 10 to the 12th. Quite a bit. Do your calculations. That's your normal stress. Shear stress tells you why. You could convince yourself again that if you're interested in some contribution of shear from the Y direction, this 13 kilonewtons, I can imagine drawing a thickness here at this point that contains D, which is perpendicular to this 13 kilonewtons. Got it? To define the variable little t. What is the area above that line that I'm currently drawing? 0. So the shear stress contribution from this 13 kilonewtons is going to be 0. That's again because it's on the surface. The outward normal is upward. The only contribution of shear that I might get is from this 9 kilonewtons that's sort of moving in the general positive x. I draw a line perpendicular to that load across the full thickness of the piece, that's here. Separate A prime. I have 2 portions that contribute to A prime, and I have a centroid associated with both of those portions. Go through all those calculations. Here's A prime, here's Y bar prime. You do those calculations. Here's that shear load coming across the face. IY is here. The thickness is 2 times the individual web thicknesses. And here's my calculation. This leads me with this 2D element That concludes the review session. Thank you for coming. Bye-bye. Thanks for coming, guys. Sorry about the internet. I just don't know what's going on. They can't handle my high latency here.